All right. Hello, everyone. My name is John Martin. Today, I'd like to talk to you about a new type of gravity model we've developed here at CU and how it can be used to enable different types of research within astrodynamics.
So to motivate this work, I'm sure everyone here knows that asteroid research is at an all-time high. And while these environments are very interesting, they're also challenging to operate in. And that's the result of their complex gravity fields, which can produce highly non-Keplerian motion. So to represent these gravity fields, people will traditionally turn to methods like spherical harmonics. But what you find is while spherical harmonics plays well for large bodies like the Earth and the Moon, it doesn't work as well for asteroids because it begins to diverge inside of the circumscribing sphere. So you'll see researchers instead turn to this polyhedral representation, which is stable down to the surface, but it requires assumptions about the density of the body. And it's also one of the most expensive representations to evaluate. So those challenges have motivated a second generation of gravity models that rely on machine learning algorithms. That includes things like extreme learning machines and Gaussian processes, and closest to my heart are these neural networks. And these are both fast to evaluate and stable down to the surface of the asteroid. So my research centers a lot on these neural network gravity models. So I just want to spend a moment explaining how you might train one. In the simplest case, you should just take some position data and some acceleration data and learn a mapping between those two using gradient descent and the following cost function. And while this method will work fine, it's not entirely satisfying because this network has no knowledge of the underlying dynamics of a gravitational system. So what I mean by that is you and I know that accelerations are really a byproduct of the scalar potential. And the scalar potential has to satisfy Laplace's equation outside of the body. The vector field that potential produces has to be conservative in nature. So we have all of this additional dynamical information that the neural network doesn't. So how do we change that? And one of the ways of doing that is using something called a physics-informed neural network, which takes each of these differential equations and constraints and embeds them into the cost function of the original network. And in this way, you end up getting a network that has to satisfy the underlying physics. And this gives increased sample efficiency, higher accuracy, robustness to noise, collection of other things that we're very excited about that we don't have time to talk about here. But what I'm trying to convey here is we have a powerful new gravity model. And the question that this paper tries to address is, what can we do with it? So to start, I just want to make this broad claim that everyone needs a good gravity model. And too often do we turn to simple constructions just because they offer creature comforts. They're easy to evaluate or play well with analytical formulations. But I'm here to argue that pins can provide all of those same creature comforts without unnecessarily simplifying the dynamics of your problem. So to showcase that, we have two applications, and the first is in reinforcement learning. And I don't want to belabor this point. I'm sure many are familiar with reinforcement learning, but the goal here is to train some agent to satisfy some high-level objectives. And you do this by having the agent interact with typically a simulated environment. So these environments can be expensive to represent and to evaluate. Take, for instance, a polyhedral model. That would be challenging to run many times, but a pin can alleviate some of those computational burdens. So let's root this in an actual example here. Consider a spacecraft that is in orbit around an asteroid, and it's just begun a mission critical operation. You're going down for a touch and go maneuver. And in the middle of this operation, as your spacecraft's drifting towards virtually a collision course with the asteroid, you lose communications. And that triggers the spacecraft to enter safe mode, which is a vegetative power positive state. And you have now just changed a tag operation to a guaranteed collision. Ideally, we want to enhance this in safe mode to ensure that when you need to diagnose a problem, you're not destining your spacecraft to intersect the body. So explicitly, we want some control solution that prevents the spacecraft from colliding with the body, keeps the spacecraft in orbit, and it conserves fuel at the same time. And writing some explicit control solution, it would be challenging for these high-level objectives. So we can reframe it as a reinforcement learning problem. We can make this a reward function instead and train an agent to interact with the environment and learn which behaviors are safe and which are unsafe. So we do that using a soft actor critic algorithm, and the action space for this agent is continuous. It can take any impulsive delta V so long as it is less than 10 centimeters per second, and it can do that once every 10 minutes. So how do pins fit into this equation? As I mentioned, you can use different gravity models for your environment, and that's going to have different effects on your performance. So normally you would think to use a polyhedral model in this case that gives you the highest fidelity dynamics, but it does come with a high computational cost. So your agent won't have many interactions with your environment. Option 2 is to have an environment that uses a point mass gravity model, which is going to be way faster to evaluate many interactions with your environment, but the dynamics aren't necessarily accurate. And the third option is hopefully the best of both worlds, and that's to use a pin, which gives you full fidelity dynamics and fast evaluation speeds. So we train the agent in each of these environments, and the performance is as follows. So let's start down here with the red curve, which is the polyhedral model. What you find is after 3 hours of training, your agent has interacted with the environment less than 2,000 times, which is not very much training data. So your agent never learns safe behavior. There's just not enough interactions with the environment. The simple gravity model agent, that achieves more than 200,000 steps in that 3 hour period, but the dynamics were inaccurate, so it was also unable to learn safe behavior. The only agent that was able to achieve, safety was the one trained with the pin as the backend. And that's because it was able to achieve both, like 150,000 interactions with the environment with full fidelity dynamics. So what those solutions look like in the case for the pin, you see that it performs a slight corrective burn here at the end, and then it manages to sit on this quasi-stable orbit for over 24 hours, potentially longer, without colliding and without running out of fuel. So this is just to say pins can help generate robust agents as compared to environments that don't use the full fidelity dynamics. The second application we look at here is the identification of near periodic orbits. As I mentioned, motion is highly non-Keplerian about asteroids. And if you were to just randomly choose an initial condition and propagate it forward, it's extremely unlikely that you'll find an orbit that returns to the same initial state or even close to the initial state. But nevertheless, we search for those conditions. And we do that using two methods. Normally, we use Lagrange planetary equations and boundary value problem solvers. And these Lagrange planetary equations, they work well if you have an analytically expressible form of the potential, like a coarse spherical harmonic model. And then you can solve these equations to find conditions where the orbit elements are fixed on average or over some period. But again, it comes with this requirement that you have an expressible potential, which isn't always true. Boundary value problems are able to compensate for when you don't have an expressible potential, but they're very sensitive to initial conditions. So what you'll see researchers do is combine these two methods. They'll use solutions to Lagrange planetary equations with a coarse gravity model, and they'll plug it into a boundary value problem with a full fidelity gravity model using those initial conditions, and they'll iterate. And this works decently well, but it does limit your search space and consequently trade space when you're designing these trajectories. So the question we asked is, do we really have to limit our search space to solutions of Lagrange planetary equations, or do we just need a better gravity model such that the boundary value problem solver can run more efficiently? What we find is the second option is actually true. If you just use a pin gravity model as the backend for the boundary value problem solver, you can find twice as many near periodic orbits than just random guessing. And that's 10 times more orbits than if you use a polyhedral model, which can't find a solution in a reasonable amount of time at all because it's so expensive to evaluate. So some of the solutions end up looking, again, very close to periodic, not quite. There are small discontinuities, but these orbits are going to maintain or require significantly less station keeping, and they're desirable in that sense. So we think this is just the tip of the iceberg. There's a lot more variations on this problem that we're interested in exploring, but we just wanted to show you some of the early findings here, just to highlight that we think pin gravity models are versatile tools capable of assisting many people solving many different astrodynamics problems. We just chose to highlight two here, which are reinforcement learning and boundary value problem solvers. But we're excited to see what more we can do in the coming months. And we hope the community finds this equally interesting as we do. So thanks for listening.